The function, denoted f of x, is called a probability distribution function, PDF. F of x is equal to the probability of x. F of x is the height of the distribution at x. In Chapter 5, the probability of x being less than 4 may be equal to the probability of x being less than or equal to 4, or not. Whether these inequalities equal or not depends on the particular probability distribution function. This is because x is a discrete random variable in Chapter 5. An example of one is the number of cans of Coca-Cola sold by your local gas station. In Chapter 6, x is a continuous random variable. The volume of gasoline sold by the gas station is an example of a continuous random variable. As a result, f of x is a probability density function, a PDF. F of x is no longer the probability of x, but areas under f's graph represent probabilities. F of x is the height of the distribution at x. In Chapter 6, the probability of x being less than 4 is equal to the probability of x being less than or equal to 4. When x is continuous, f of x is not equal to the probability of x, but areas under f's graph represents probabilities. The probability of a random variable, assuming a value within some given interval from x1 to x2, is defined to be the area under the graph of the probability density function that is between x1 and x2. Using statistics notation, write the above as the following. For the uniform distribution, the probability of being between x1 and x2 is the area of the red rectangle. To find this area, we multiply the height by the width, which is x2 minus x1. For the normal distribution, it's more complicated. To compute the probabilities under this curve, we use the standard normal table that is on the inside of most statistics textbooks or in the appendix of the book. For the exponential distribution, we use an equation to compute the area. We don't use the probability density function. This function is used to graph the distribution. Instead, we use the cumulative density function. A random variable is uniformly distributed whenever the probability is proportional to the interval's length. In Chapter 5, we looked at a uniform discrete probability distribution function. Here we're talking about the uniform probability density function because here x is a continuous random variable. The uniform probability density function is f of x is equal to 1 divided by the quantity of b minus a, where a is the smallest value the variable can assume. B is the largest value the variable can assume. The expected value of the uniform distribution is equal to the quantity of a plus b divided by 2. This is a shortcut to the expected value, similar to the shortcuts that were used to compute the expected values of discrete random variables in Chapter 5. The variance of the uniform distribution is equal to b minus a squared divided by 12. Slater customers are charged for the amount of salad they take. Sampling suggests that the amount of salad taken is uniformly distributed between 5 and 15 ounces. Note in Chapter 13 we actually test the validity of this assumption. Write down what we know. B equals 15. A equals 5. F of x equals 1 divided by the quantity b minus a, which is equal to 1 divided by 15 minus 5, or 1 divided by 10. Now this looks familiar. It looks a lot like the uniform discrete probability distribution. X equals salad plate filling weight. The expected value of the uniform distribution is equal to the quantity of A plus B divided by 2, which is equal to the quantity of 5 plus 15 divided by 2, or 10 ounces. The variance of the uniform distribution is equal to b minus a squared divided by 12, or 15 minus 5 squared divided by 12, which is 8.3 ounces squared. The standard deviation is the positive square root of the variance, which can be computed by raising 8.33 to the 0.05 power, which is equal to 2.886 ounces. The variance is in ounces squared. The standard deviation is in ounces. To graph the distribution, first label the range of the variable and its height. So the range of the random variable is 5 to 15. The height of this distribution is always 1 over 10. Now draw lines up to the height of 1/10, and then shade the resulting rectangle gray. This gray area is the uniform probability distribution. Notice that the expected value separates the distribution into halves. The expected value is 10, if you recall. This is because the uniform distribution is symmetric. Question: what is the probability that a customer will take between 12 and 15 ounces of salad? In statistics notation, we want the probability that x is between 12 and 15. Since the interval for this probability is from 12 to 15, we label the 12 on the number line. Then draw a vertical line up to the height of the distribution. The area under this distribution is shaded in red. There, the red rectangle is equal to its height times its width. Since the width of the red rectangle is 15 minus 12, or 3, we multiply the distribution's height of 1/10 by 3. Hence, the probability that a customer will take between 12 and 15 ounces of salad is 0.3. Question: what is the probability that a customer will take exactly 12 ounces of salad? In statistics notation, we denote this as P of x equal 12, and read that as the probability that x equals 12. If we compute this probability as if we were computing the area of a rectangle under this graph, the rectangle would have a width equal to 12 minus 12, or 0. The area of the red rectangle is equal to its height times its width. Since the width of the red rectangle is 0, we multiply the distribution's height of 1/10 by 0. The probability of a customer taking exactly 12 ounces of salad is 0. In Chapter 6, when we're talking about continuous random variables, the probability that x equals a number is always equal to 0. The normal probability distribution is the most common distribution for describing a continuous random variable. It is widely used in statistical inference. It has been used in a wide variety of applications, including heights of people, test scores, rainfall amounts, scientific measurements, production lines, like, for example, filling Coke bottles. In Chapter 6, the distribution will be given. If x has a uniform distribution, its endpoints, a and b, will be given. If x is a random variable having a normal distribution, its mean, denoted mu, and its standard deviation, denoted sigma, will be given. The normal probability density function is given by the following equation, where pi is approximately equal to 3.14159, e is approximately equal to 2.71828. The normal distribution is symmetric, so its skew is equal to 0. The normal distribution is bell-shaped. When drawing a normal distribution, you must label the standard deviation, sigma, and mean, mu. The mean tells you the location of the center of the distribution on the number line, while sigma determines the height and width of the distribution. Notice the expression in red up here in the exponent of e. X minus mu divided by sigma, well, that's just the z-score. So if we replace this red value with z and replace that with z, we get the standard normal distribution, but more on that in a second. The mean of a normal distribution could be any numerical value. Suppose we hold the standard deviation sigma equal to 2, but allow the mean to change from mu equal 4 to mu equal 6 to mu equal 8. Under all three scenarios, the height and width of the distributions were equal because the standard deviations were all equal. The only difference between the distributions was where their centers were located. Well, the mean determines the location of the distribution center. The standard deviation determines how tall it is and how wide it is. Suppose we hold the mean of the normal distribution equal to 6, but increase the standard deviation from sigma equal 2 to sigma equal 3 to sigma equal 4. Under all three scenarios, the center of the distributions all remain at mu equals 6, but the height falls as width increases as sigma increases. The standard normal distribution is a normal distribution with a mean mu equal to 0 and a standard deviation sigma equal to 1. Typically, the letter z is used to denote a random variable that has this distribution, while x is used to denote a random variable having some other normal distribution. Z is used, I think, because remember what the z-score was? The z-score in a previous chapter was the standardized value. When you compute z-scores, you demean the variable x, and you give the new variable a standard deviation of 1. The following is the normal distributions function, but x has been replaced with letter z. Here we have replaced mu with 0 and sigma with 1 because z is the standard normal distribution with mean mu equal to 0 and standard deviation sigma equal to 1. Simplifying yields the equation for the standard normal probability distribution function. When you look at this distribution, it looks like a bell, which is why it's called a bell-shaped curve. It is centered at 0, and the horizontal axis is labeled z. Notice that z is on the horizontal axis. The mean is 0, and we've labeled the height and width of the distribution sigma equal 1 because the standard deviation of standard normal is 1. We can use the standard deviation table located on the inside cover of most textbooks to verify the empirical rule. 68.26% of values of a normal random variable are within one standard deviation of its mean. 95.44% of values of a normal random variable are within two standard deviations of its mean. Nearly all, or 99.74% of values of a random normal variable are within three standard deviations of its mean. So let's compute the probability of being within three standard deviations of the mean. Since z's mean is 0 and its standard deviation is equal to 1, negative 3 is 3 standard deviations below z's mean of 0. Because negative 3 is less than 0, we label it to the left of the distribution's center at 0. The red arrow represents the probability of being less than or equal to negative 3. To compute the probability that z is less than or equal to negative 3, go to row negative 3.0 in the standard normal table that is on the inside of most statistics textbooks, and then go to column 0.00. The intersection of row negative 3.0 and column 0.00 is 0.0013. Thus, the probability that z is less than or equal to negative 3 is equal to 0.0013. After getting the probability from the table, label the lower red tail probability with 0.0013. Now, compute the upper tail probability. To compute the probability that z is less than or equal to 3, go to row 3.0 in the standard normal table that is on the inside cover of most statistics books. Then go to column 0.00. The intersection of row 3.0 and column 0.00 is 0.9987. Hence, the probability that z is less than or equal to 3 is 0.9987. After getting the probability from the table, label the gray area 0.9987, since the probability of being less than or equal to 3 is 0.9987. Since we want to know the probability of being greater than or equal to 3, we use the complement rule. Thus, the probability of being greater than or equal to 3 is 1 minus 0.9987, which is equal to 0.0013. This is the same value as the probability of being less than or equal to negative 3, which is in the area of the lower tail of the distribution. This results from the distribution being symmetric about the mean of 0. If the lower and upper tail probabilities both equal 0.0013, the area in the tails is equal to 0.0026. Using the complement rule again, the probability of being inside the tails is equal to 1 minus 0.0026, which equals 0.9974. Hence, 99.74% of values of a normal random variable are within 3 standard deviations of its mean. Now compute the probability of being within 2 standard deviations of the mean. To do this, first compute the probability that z is less than or equal to negative 2. Because z's mean is 0 and its standard deviation is equal to 1, negative 2 is 2 standard deviations below z's mean of 0. Since negative 2 is less than 0, we label it to the left of the distribution center at 0. The red area represents the probability of being less than or equal to negative 2. To compute the probability that z is less than or equal to negative 2, go to row negative 2.0 in the standard normal table, then go to column 0.00, the intersection of row negative 2.0 and column 0.00 is 0.0228. Hence, the probability that z is less than or equal to negative 2 is 0.0228. After getting the probability from the table, label the left lower red tail probability 0.0228. Now compute the upper tail probability. To compute the upper tail probability, or to compute the probability that z is less than or equal to 2, go to row 2.0, column 0.00. The intersection of this column and that row is 0.9772. The probability of z being less than or equal to 2 is 0.9772. After getting the probability from the table, label the gray area 0.9772. Because the probability of being less than or equal to 2 is 0.9772. Because we want to know the probability of being greater than or equal to 2, we use the complement rule. Thus, the probability of being greater than or equal to 2 is 1 minus 0.9772, which is 0.0228. This is the same value of the probability of being less than or equal to negative 2, which is in the area in the lower tail of the distribution. This is because the distribution is symmetric about the mean of 0. If the lower and upper tail probabilities are both equal to 0.0228, the area in the tails is 0.0456. Using the complement rule again, the probability of being inside the tails is equal to 1 minus 0.0456, which equals 0.9544. Hence, 95.44% of values of a normal random variable within 2 standard deviations of its mean. Compute the probability of being within 1 standard deviation of the mean. To do this, first compute the probability that z is less than or equal to negative 1. Since z's mean is 0 and its standard deviation is equal to 1, negative 1 is 1 standard deviation below z's mean of 0. Because negative 1 is less than 0, we label it to the left of the distribution center at 0. The red area represents the probability of being less than or equal to negative 1. To compute the probability that z is less than or equal to negative 1, go to row negative 1.0, column 0.00, the intersection of column 0.00 and row -1.0 is 0.1587. Thus, the probability that z is less than or equal to -1 equals 0.1587. After getting the probability from the table, label the lower red tail probability with 0.1587. Now compute the upper tail probability. To compute the probability that z is less than or equal to 1, go to row 1.0, column 00. The intersection of column 0.00 and row 1.0 is 0.8413. The probability that z is less than or equal to 1 is equal to 0.8413. After getting the probability from the table, label the gray area 0.8413 since the probability of being less than or equal to 1 is 0.8413. Since we want to know what the probability of being greater than 1 is, we use the complement rule. Thus, the probability of being greater than or equal to 1 is 1 minus 0.8413, which is equal to 0.1587. This is the same value that is in the lower tail probability. And this is because, again, the distribution is symmetric. If the lower and upper tail probabilities both equal 0.1587, the area in the tails is 0.3174. Using the complement rule again, the probability of being inside the tails is equal to 1 minus 0.3174, which equals 0.6826. Thus, 68.26% of values of a normal random variable are within one standard deviation of its mean. Hence, the empirical rule is verified. As we have seen, probabilities for the normal random variable are given by areas under the curve. Verify the following. The area to the left of the mean is 0.5. In other words, we want to verify that the probability of z is less than or equal to 0 is equal to 0.5. To compute the probability that z is less than or equal to 0, go to row 0.0 in the standard normal table, then go to column 0.00. The intersection of row 0 and 0.00 is 0.5000. Hence, the probability that z is less than or equal to 0 equals 0.5000. The red area takes up half the distribution because the probability that z is less than or equal to 0 equals 0.5. Now verify the following. The area to the right of the mean is 0.5. We know that the probability that z is less than 0 is equal to 0.500. We use the complement rule to find the probability that z is greater than 0, which is equal to 1 minus 0.500, which is just 0.5000. Thus, the probability that z is greater than 0 is 0.500. The total area under the curve is 1, because all we have to do is add 0.500 and 0.500, and we get 1. What is the probability that z is less than or equal to negative 2.76? In notation, we write the probability z less than or equal to negative 2.76. Because 2.76 is less than 0, we label it left of 0. The red area represents the probability that z is less than negative 2.76. To compute the probability that z is less than or equal to negative 2.76, go to row negative 2.7 and column 0.06. The intersection of row negative 2.7 and column 06 is 0.0029. Thus, the probability that z is less than or equal to negative 2.76 equals 0.0029. Because the probability that z is less than or equal to 2.76 is 0.0029, we shade the red lower tail probability 0.0029. Now, what is the probability that z is less than negative 2.76? It is equal to 0.0029 since z is a continuous random variable, and the probability that z equals exactly equals negative 2.76 is 0. What is the probability that z is greater than or equal to negative 2.76? To compute this, we use the complement rule. 1 minus 0.0029 is equal to 0.9971. Thus, the probability that z is greater than or equal to negative 2.76 is equal to 0.9971, which is represented by the gray area under the curve. Now, what is the probability that z is greater than negative 2.76? The probability that z is greater than negative 2.76 is 0.9971 because z is a continuous random variable, and the probability of any continuous random variable equaling an exact value is 0. What is the probability that z is less than or equal to 2.87? In notation, we write the probability that z is less than or equal to 2.87, which is the red area. To compute the probability that z is less than or equal to 2.87, we go to row 2.8, column 07. The intersection of these two rows and columns is 0.9979. Thus, the probability that z is less than or equal to 2.87 is 0.997. We label the red area 0.9979. So the probability that z is less than or equal to 2.87, again, is 0.9979. What is the probability that z is less than 2.87? It's 0.9971 because z is a continuous random variable, which means the probability that z is less than 2.87 is the same as the probability that z is less than or equal to 2.87. What is the probability that z is greater than or equal to 2.87? To compute this probability, we use the complement rule. 1 minus 0.9979 is equal to 0.0021. Hence, the probability that z is greater than or equal to 2.87 is equal to 0.0021, which is represented by the gray area under the curve. What is the probability that z is greater than 2.87? It is equal to 0.0021 because z is a continuous random variable, and the probability that z exactly equals 2.87 is 0. What is the value of z if the probability of being smaller than it is equal to 0.0250? In statistics, we write it as the following. The probability of z less than or equal to question mark equals 0.0250. Because we want to find the z-value that is associated with a lower tail probability of 0.0250, we shade the lower part of the distribution red and label this area 0.0250. If this said bigger, or this was greater than or equal to, we would have shaded the upper tail probability corresponding to 0.0250. To find the value of z that is associated with the lower tail probability of 0.0250, find 0.0250 in the standard normal table. 0.0250 is in row minus 1.9 and column 0.06. Hence, the probability of z being less than negative 1.96 is equal to 0.0250. So z is equal to a negative 1.96. So z is equal to a negative 1.96. What is the value of z if the probability of being greater than it is 0.0192? In statistics notation, we write this as the probability of z greater than question mark equal to 0.0192. The greater than and the word greater indicate we're talking about an upper tail probability. Because we want to find the z-value that is associated with an upper tail probability of 0.0192, we shade the upper part of the distribution red and label this area 0.0192. Because the standard normal table gives us lower tail probabilities, we use the complement rule before we proceed. 1 minus 0.0192 equals 0.9808. To find the z-value, we need to answer this question. What is the value of z if the probability of being less than it is 0.9808? So we find 0.9808 in the z table. It is in row 2.0 and column 0.07. Thus the probability of z being less than 2.07 is equal to 0.908. So z is equal to 2.07. What is the value of minus z and z? The probability of being between them is 0.9500. If the area in the middle is 0.95, then the area not in the middle is 0.05. And so each tail has an area of 0.025. 0.025 plus 0.025 equals 0.05. So the area in the tails is 0.05. The area not in the tails is 0.95. So the probability of being between negative z and z is 0.95, which is the gray area. To find negative z, when the probability of being between it and z is 0.95, we have to find 0.0250 in the standard normal table because the probability of being less than negative z is 0.0250. 0.0250 is in row negative 1.9 and column 06. Thus, the probability of z being less than minus 1.96 is equal to 0.250. So negative z is equal to negative 1.96. The lower tail probability of 0.0250 is associated with a negative z value equal to negative 1.96. By symmetry, the upper z value is 1.96. Z is a random variable that is normally distributed with a mean of 0 and a standard deviation of 1. X is a random variable that is normally distributed with a mean of mu, unknown, and a standard deviation of sigma, unknown. Because there are infinite many choices for mu and sigma, it would be impossible to have more than one normal distribution table in the textbook. To handle this, we simply convert x to z using the z-score. We're going to standardize x. We're going to demean x and then change its standard deviation from sigma to 1. Recall that the z-score is just the deviation from the mean divided by the standard deviation. We can think of z as a measure of the number of standard deviations x is from the mean. Pepzone sells auto parts and auto supplies, including a popular multi-grade motor oil. When the stock of this oil drops below 20 gallons, a replenishment order is made. The store manager is concerned that sales are lost due to stockouts while waiting for a replenishment order. It has been determined that demand during the replenishment lead time is normally distributed with a mean of 15 gallons, standard deviation equal to 6 gallons. The manager would like to know the probability of a stockout during replenishment lead time. In other words, the manager wants to know the probability that a demand during lead time will exceed 20 gallons. X is demand during lead time, and the manager wants to know if it exceeds 20 gallons. We're going to use a step-by-step procedure to compute this probability. Step 1, draw and label the distribution. Because the distribution is normal, the distribution has a bell shape whose center is at 15. The standard deviation tells us how wide and tall the distribution is. Because we want to know the probability that x is greater than 20, we label 20 just to the right of 15. Draw a vertical line up to the curve, and then shade everything to the right of this line. Note, the red area should be less than 0.5. If not, a mistake has been made. In step 2, we convert x to standard normal distribution using the z-score to do this, which is equal to the deviation from the mean divided by the standard deviation. In this example, it would be 20, the value here, minus 15 divided by the standard deviation 6, which is 0.83. What that says is 20 is $5 above the mean. In terms of standard deviation, 20 is 0.83 standard deviations above the mean. So the z value is equal to 0.83. Because it is equal to 0.83 and its mean is 0, the probability that x is greater than 20 is equal to the probability that z is greater than 0.83. Because the standard normal table gives us lower tail probabilities, we need the probability that z is less than 0.83. which is represented by the gray area. Step 3, find the area under the standard normal curve to the left of z equal to 0.83. To find this probability, go to row 0.8 in the standard normal table, and then go down column 0.03. The intersection of row 0.8 and column 0.03 is 0.7967. Thus, the probability that z is less than or equal to 0.83 is 0.7967. Step 4, compute the area under the standard normal curve to the right of z equal to 0.83. Because the probability that z is less than or equal to 0.83 is 0.7967, we label the gray area 0.7967. The probability that x is greater than 20 is equal to the probability that z is greater than 0.83, which is equal to 1 minus 0.7967, or 0.2033. Hence, the probability of a stockout during replenishment lead time is 0.2033. If the manager of PepZone wants the probability of a stockout during replenishment lead time to be no more than 0.05, what should the reorder point be? In this problem, we want to know what x1 is equal to, where x1 is a numerical value such that the probability that x is greater than it is 0.05000. Because we want to find the number x1 such that the probability of being greater than it is equal to 0.05, we shade the upper tail of the distribution and label 0.05. If the area in the red upper tail equals 0.05, the gray area under the curve equals 0.95. The value we are looking for is x1, which is the value such that the probability of being less than it is equal to 0.95. Because we do not have a probability table for a normal distribution with a mean of 15 and a standard deviation of 6, we have to convert x to z using z-score. z1 equals the deviation in the mean divided by the standard deviation. Substituting the values of mu and sigma yields the quantity x1 minus 15 divided by 6. To solve this for x1, we first multiply both sides by 6. This cancels out 6 on the right-hand side. Then we add 15 to both sides, which results in x1 equal to 15 plus 6 times z1. Once z1 is determined, x1 can be computed. To find z1, we turn to the standard normal distribution and its probability table. The standard normal distribution is a mean 0 and a standard deviation equal to 1. z1 is the value that cuts off an area 0.95 on the left and 0.05 on the right. To find z1, find the z value that cuts off an area of 0.05 in the right of the standard normal table. However, the standard normal table gives left tail probabilities instead. We want the z value that cuts off an area 0.95 in the left tail. Because 0.95 is not in the standard normal table, we find the closest value or values. The closest two values are 0.9495 and 0.9505. Both are equally good candidates. These probability values are in row 1.6 and columns 0.04 and 05. Thus, there are two equally good values for z, 1.64 and 1.65. Averaging these values yields the z value of 1.645. Recall that once z1 is determined, x1 can be computed. Substituting 1.645 in for z1 yields x1 equal to 15 plus 6 times 1.645, or x1 equal to 24.87. So 24.87 gallons is the value such that the probability of being greater than it is equal to 0.05. Hence, a reorder point of 24.87 gallons will place the probability of a stockout at 5%. The exponential probability distribution is useful in describing the time it takes to complete a task. Exponential random variables can be used to describe time between vehicle arrivals at a toll booth, distance between major defects in a highway, time required to complete a questionnaire. The exponential probability density function is f of x equal to e raised to the ratio of negative x and mu divided by mu, where mu is the mean, which must be positive, e is the natural number, 2.71828 approximately, and x is a random variable that cannot take on negative values. Unlike the normal distribution, the exponential probability density function is well behaved, meaning it has a cumulative probability function. Now, the cumulative probability function actually comes from, if anybody's ever had calculus, it comes from integrating the PDF over x. Using the exponential cumulative probability function is analogous to using a standard normal table because it computes left tail probabilities, where x0 is some specific value of x, mu is the mean, which is positive, and e is approximately 2.71828. The time between arrivals of cars at Al's full-service gas pump follows an exponential probability distribution with mean time of arrivals equal to 3 minutes. I would like to know the probability that the time between two successful arrivals will be 2 minutes or less. In statistics notation, we write this as, what is the probability that x will be less than 2? Note x0 is equal to 2 in this problem, and mu equals 3. The graph of this exponential distribution is given below. Since we want to know the probability that x is less than 2, we draw a vertical line up to the curve, and then shade the area to the left of this line. If the random variable was normally distributed, we'd have to compute the z value of x, and look up this value in the standard normal table. However, since x is an exponential random variable, we can use the cumulative probability function. With x0 equal to 2, we substitute this into the equation, which equals 1 minus 0.5134, or 0.4866. The probability of being greater than x0 is equal to e raised to the ratio of minus x0 and mu, which in this case is 0.5134. So this white area is 0.5134.